Object detection sounds complicated, but it actually starts with something more simpler. Edge detection. Let's see how OpenCV finds edges in an image and why that's the foundation of object detection. First, I'm going to import OpenCV and matplotlib. OpenCV handles reading and processing the image, and matplotlib lets us safely display it inside a Jupyter notebook. When OpenCV reads an image, it uses BGR color ordering, so before displaying it, we convert it to RGB because matplotlib expects RGB. Before applying canny edge detection, I convert the image to grayscale. This is good practice because canny is defined on intensity, not color, which gives us predictable and well-defined edge detection. Finally, I apply the canny edge detector, and there we go, the edges in the image are clearly identified. But wait, what are these two parameters? The two canny parameters are just thresholds that control what counts as an edge. If I make the first threshold lower, more weak edges will be considered, which can include noise. If I make the second threshold higher, only very strong edges will be kept, which makes the result cleaner, but can remove some detail. But like always, I think implementing things ourselves really helps us understand what's going on. So instead of using a canny edge detector, let's build a simple edge detector ourselves. Since canny is a bit more complicated, we'll start with Sobel. There isn't a single Sobel edge detector function like there is for canny. Sobel just computes image gradients in the x and y directions using convolution kernels. When I apply the Sobel filter in the x direction, it's measuring how pixel values change from left to right. That means it highlights vertical edges, which is why you see these little vertical lines popping out in the image here. When I switch to the y direction, Sobel measures changes from top to bottom instead. So now horizontal edges are emphasized, and you can see those horizontal lines becoming much more visible. Now I'm going to combine both directions by taking the square root of the x and y gradients squared. This gives us the overall gradient magnitude, meaning we're measuring how strong the intensity change is at each pixel, regardless of direction. When we visualize this, we get a full edge map where both horizontal and vertical edges show up together. Using OpenCV's Sobel function to compute image gradients is cool, and it's great for quickly seeing the results. But to really understand what's happening here, it helps to build this ourselves. Instead of relying on this built-in function, let's implement our own edge detection by explicitly defining the Sobel kernels and applying them using convolution. First, I'm going to define my Sobel kernels. But you might be wondering, why do they look like this? Let's walk through a quick example. If I take the x direction kernel and apply it to this pixel neighborhood, multiplying element-wise and summing the result, I get 0. That tells us there's no left to right intensity change here. So this isn't a vertical edge, which makes sense. The y direction kernel is just the transpose of the x kernel. When I apply it to the same pixel neighborhood, I get a large value, indicating a strong top to bottom intensity change. That tells us this is likely a horizontal edge, which also makes sense. Now we need to apply these kernels to every pixel in the image. So I'm going to write a simple convolution function. This function takes in an image and a kernel and returns a new image after applying the kernel everywhere. First, we grab the height and width of the image so we know how many pixels we need to process. Then we get the height and width of the kernel so we know the size of the window will be sliding across the image. From that, we compute how much padding is needed so the kernel can be centered on every pixel. Next, we pad the image by extending the edge values, which allows us to apply the kernel even at the borders without shrinking the image. We also create an empty output image where we'll store the result of the convolution. Then we loop over every pixel location in the image. At each location, we extract the local neighborhood that matches the size of the kernel, multiply it element by element with the kernel, sum the result, and store that value in the output image. Finally, we return the output image, which now represents how strongly the kernel responds at each pixel location. So in the end, edge detection is really just about measuring how pixel values change across an image. By understanding how simple filters like Sobel work under the hood, it becomes much clearer how more advanced edge detectors like canny are built on top of these same ideas.